Have you ever wondered how the physical silicon chips that run our entire world are actually designed? We're talking about the hardware in your phone and your computer in the cloud. Well, today we're diving into Verilog. It's the language that lets us literally write hardware into existence. Let's get right into it. So just think about this for a second. How in the world do you even begin to design a modern microchip? We're talking about billions with a B of tiny little transistors. The scale is it's mind-boggling. You obviously can't draw that out by hand. So, how is it done? Well, the trick is to stop thinking about individual transistors. Instead, the approach is to think of it like building with digital Legos. Designers don't work with single dots. They work with pre-made functional blocks that they can snap together to build something way, way bigger.
And that's exactly where Verilog comes into the picture. It's a hardware description language, or HDL. Now, this is a really important point. It's not a programming language like Python or C++. It's a description language. It's the literal blueprint that describes, in text, how to build and connect all of our digital Legos.
So here's our game plan for today. We're going to start with the most basic building block, figure out how to connect them, then how to give them a job to do, make them reusable so we're not repeating ourselves, and finally, we'll see how all this code actually becomes a real physical thing. All right, first up, let's talk about the absolute most fundamental piece of the puzzle in Verilog, the module. A module is the basic unit of any Verilog design. You can just think of it as a single, self-contained Lego brick. It's designed to do one specific thing, and it's the foundation for everything else we're going to build.
And this is how we start building cool stuff. You can take these individual modules, these little Lego bricks, and place them inside of other bigger modules. The fancy word for this is instantiation, but it's really just like taking a few small Lego kits and combining them to build one giant, awesome creation. This is how you build up a complex hierarchy, where one main top module holds everything else. So we've got our Lego bricks, our modules. The next logical question is, okay, how do we actually snap them together?
We connect them using things called ports. A port is simply the interface of a module. It's the set of connection points for inputs and outputs. Sticking with our analogy, ports are literally the studs on the top of the Lego and the holes on the bottom. They're what allow the bricks to physically connect and communicate with each other. Now, when it comes to actually wiring up these modules, Verilog gives you two choices. You could connect them by order, which means the first wire in your list connects to the first port, the second to the second, and so on. It's simple, sure, but it's also super risky. Imagine you have 50 ports and you get just one out of order. It's an absolute nightmare to find that bug. That's why the professional recommended way is connecting by name. You explicitly say, this wire connects to that port. It's clear, it's safe, and it'll save you a world of hurt down the line.
Okay, so far, everything we've built is just a static structure. It's like a Lego model sitting on a shelf. But how do we make it actually do something? Let's talk about adding logic and behavior. We make our design come alive using what are called procedural blocks. There's the initial block, which, you guessed it, runs just one time right at the beginning. Perfect for setting things up. Then there's the always block. This one runs over and over again, usually triggered by something like a clock signal. And here's the really crucial part, the thing you have to wrap your head around. All of these blocks in your design run at the same time. They execute concurrently, in parallel, which is exactly how real hardware works. Okay, that brings up a really, really important question. If everything is happening in parallel, how do we safely change the value of a variable inside one of these blocks without causing total chaos? The way Verilog handles this is one of its most critical concepts. So, Verilog gives us two types of assignments. First, you've got the blocking assignment, which just uses a regular equal sign. This works like you'd expect in most programming languages. Line 1 finishes, then line 2 starts. It's sequential. But the real secret sauce for hardware design is the non-blocking assignment, which uses this less than or equal to symbol. This is how you model things happening in parallel. It essentially tells the system, figure out all these new values, and then update them all at the exact same time. This is key to modeling how real circuits behave.
So how does that non-blocking magic actually work under the hood? It's a really elegant two-step process. First, at a specific moment in time, the simulator looks at the right-hand side of all your non-blocking assignments and calculates the new results. Then, it schedules these new values to be updated. And finally, in the third step, all those variables on the left-hand side get their new values simultaneously.
It's this little evaluate then update dance that lets Verilog perfectly model parallel operations in hardware. You know, good engineers are lazy in the best way possible. They don't reinvent the wheel every single time. They build flexible, reusable blueprints. Let's see how Verilog makes that easy. One of the best tools for this is called a parameter. A parameter is basically a constant that you define inside your module, like, say, the width of a databus. The cool part is, when you go to use that module somewhere else, you can easily change that value. It's just like having an adjustable Lego brick. You design it once, but every time you use it, you can say, okay, this time I need you to be 8 bits wide, or this time make it 64. It's incredibly powerful for creating flexible designs. Now, for dealing with smaller, repeating patterns of code inside a single module, Verilog gives us 2 more handy tools: functions and tasks. They both help you write cleaner code and avoid repetition, but they're used for very different situations. This chart breaks it down perfectly. A function is the simple one. It has to have at least one input, it gives you exactly one output back, and, this is key, it can't have any time delays. This makes functions perfect for modeling simple, instantaneous logic, like a math calculation. A task, on the other hand, is the powerhouse. It can have any number of inputs or outputs, and it can contain time delays. This allows tasks to model much more complex sequences of operations. All right, we've come a long way. We've designed our modules, we've connected them with ports, and we've given them behavior. So, how does this text file, this abstract blueprint, become a real physical microchip? Well, it happens through a process that honestly feels like magic. It's called synthesis. A special piece of software, a synthesis tool, reads your Verilog code, understands the behavior and structure you've described, and then translates it into something called a netlist. And a netlist is basically the final set of construction plans. It's a literal, detailed map of all the basic logic gates, the ands, the ors, the nots, and all the tiny wires that connect them. And just like that, the journey is complete. The abstract blueprint you wrote in a text editor gets turned into a concrete plan. Your digital Lego creation is transformed into a real, physical, electronic circuit that's ready to be manufactured on a piece of silicon. So the really big idea here is that we've moved from physically drawing circuits to describing them with language. And that leaves us with a pretty profound question to think about. If the very fabric of our digital world, the physical hardware itself, is now written like code, what new realities are we now capable of writing into existence?